Hello wonderful person, this is Anton, and you're looking at the beautiful moon Titan, the moon of Saturn. Today we're going to be answering a question of why is it that this is actually the only moon, or really one of the two objects in the entire solar system that seems to have a stable atmosphere on the surface. How come none of the other planets except for Earth, and pretty much none of the other moons have anything remotely similar? Let's talk about this, and welcome to What the Math. This right here is the Cassini craft on September 15th, 2017, when it plummeted into the atmosphere of Saturn. This craft is the reason we know so much about both Saturn and Titan, and actually had a small partner attached to it that ended up landing on the surface of Titan and actually took some amazing photos. But all of this was mentioned in some of the previous videos. Today we're really focusing only on one thing. We're focusing on trying to understand how Titan, which is a moon that's way smaller than our planet Earth, is actually able to maintain a relatively thick atmosphere that extends even higher than the atmosphere of Earth. The atmosphere here extends up to about 1,000 kilometers, and the actual pressure on the surface of this moon is about 1.5 atmospheres, meaning that it's about 50% more than the atmospheric pressure on the surface of Earth. This atmosphere is also, just like the Earth atmosphere, predominantly made up of nitrogen, and the other 2 or so percent are usually things like methane, ethane, and a few other components. Earth atmosphere, on the other hand, is about 75% nitrogen, and the rest is oxygen and CO2 and some other things. So here we even have a tremendous amount of nitrogen, just like on Earth. And what is really interesting about this particular moon is that it resembles Earth in many different ways, including, of course, things like lakes on the surface that we've been able to detect with this radar that you see right here. We've also found all kinds of geological and atmospheric activity, very similar to planet Earth. And all in all, it has a tremendous amount of secrets that we're still yet to discover. There's even this vortex that we've detected a few years back. So, okay, so the atmosphere, how is it able to maintain this? Because none of the other moons that have a similar interior structure, meaning that if we look inside of this moon, we'll find things like a relatively large liquid ocean, we'll find a really thick water ice structure on top, and we'll find more ice and also silicates on the bottom, and not very much iron. In terms of structure, it's actually very similar to other moons, like, for example, Ganymede, and the actual moon itself technically should not really have any atmosphere, because if we compare this to other typical moons, let me actually just place a few here so you can see them in comparison. So here's our moon, here's Io, Ganymede, Callisto, and let's also place Europa. So these are sort of the most popular moons. None of the other moons have anything on the surface. There's very little in terms of what's known as an exosphere, and that usually refers to a very thin layer of molecules, but not an actual thick thing that you see right here. So to answer this, we actually have to think about the molecules present on the surface, and also we need to try to think about objects like Mars that used to have thick atmosphere that was then lost for one reason or another. By answering the question of why Titan has atmosphere and Mars doesn't, we'll actually be able to understand how atmospheres are maintained and how atmospheres can even be created on objects like Mars. So to start answering this, we're going to also place Earth here, which is going to be a gigantic planet in comparison to everything else, and look at what's happening here. So Earth atmosphere has a tremendous amount of nitrogen, but also oxygen, and today we're almost certain that it's the magnetosphere of Earth that essentially protects the atmosphere of our planet and prevents it from evaporating, and we believe that that's why Mars doesn't have atmosphere anymore, or has a very thin atmosphere of CO2. Essentially, it lost its magnetosphere and it was slowly stripped by the sun over time. On the other hand, Mars also has a lot less mass and thus less gravity. But then again, so does Titan. Titan's gravity is even less than Mars. And just like Mars, Titan also has no magnetosphere, so for a very long time some scientists suspected that maybe Saturn is actually protecting Titan by enveloping essentially all of the moons here with a very thick magnetic field. But that's not really what's happening here at all, and as a matter of fact, the answer is more chemical than it is related to the magnetosphere. So going back to what we know about Titan and Earth, we know that they have one thing that's pretty much in common, and that's nitrogen. Both objects have a tremendous amount of nitrogen on the surface. And on the other hand, Earth also has oxygen, but Titan has no oxygen, or at least none we've detected so far. And that's really the biggest hint here. The real reason is that oxygen is actually relatively unstable when it's exposed to the solar radiation. Specifically, here is what the molecule of nitrogen looks like. This is N2, it has a triple bond, making the molecule relatively strong. And here is O2, oxygen, that has a double bond, making the molecule slightly less strong. Now, interestingly, oxygen is slightly heavier than nitrogen, so technically speaking, the molecular weight itself is not enough to keep the oxygen on the surface of different objects. As a matter of fact, even if we put a bunch of oxygen onto the surface of Titan, it will most likely not stay here very long. So molecular weight is one thing, and the molecular bond is the other. If we also look at the actual molecular weight and compare it to the gravity of the object, and this is actually something known as Jean's law, we can actually see, or draw in a sense, a kind of a graph where you can determine what object in the solar system can maintain what type of a molecule. So for Earth and Venus, they can maintain everything including water vapor, ammonia, and methane. But they cannot maintain helium or hydrogen. That's why our planet Earth has a tremendous cloud of hydrogen and helium around it. And helium for the most part escapes and never returns. However, the gas giants and ice giants have no problem maintaining these, and for the most part they are made out of hydrogen. Then we have objects like Titan and Mars, and also Ganymede is on the list here, that can technically maintain oxygen and nitrogen, at least according to the molecular weight. And so in that sense, technically both Mars and Titan should have a relatively similar atmosphere. But for some reason or another, Mars never really got a tremendous amount of nitrogen like Earth and Titan, but it used to have oxygen, and we're pretty sure they used to have oxygen because it turned red, and the redness of Mars comes from the fact that it got oxidized by the oxygen. This is most likely iron oxide. And so this oxygen was there, but is not there anymore. And so something must have caused the oxygen to break its bond and connect to other molecules. And this something is, of course, the solar radiation. Here's what the sun's radiation spectrum looks like. And for the most part, as you can see, our sun emits mostly visible light and some infrared and a little bit of UV light. But the UV light it emits is actually relatively soft. It's not very strong. It doesn't really emit almost any hard UV light. And it just so happens that the molecule of oxygen is highly affected by the soft UV light. It can actually be broken up by the soft UV, but the molecule of nitrogen cannot. It needs to have hard UV light for it to break. So it's the solar radiation that breaks up the oxygen molecules, creating other molecules or letting oxygen escape into the outer space and basically disappear. And yet at the same time, it's the lack of hard UV light from the sun that allows nitrogen to survive on pretty much any object without any concern for its stability. So in other words, you could technically have nitrogen on every major moon and every major planet, and it would not really disappear, because sun's radiation is just not strong enough to break, for the most part, the nitrogen molecule. On the other hand, the system of Saturn is also pretty far away from the sun. It's over 9 astronomical units away from the sun, meaning that only about 1/80th or even less than that of the solar radiation reaches Titan and reaches Saturn compared to Earth. In other words, if you were to stand on the surface of Titan as opposed to standing on the surface of Earth, you would only receive about 1/80th of the radiation. So the actual strength of the solar rays here even if its hard UV rays would not be really that strong. It would not really affect the actual atmosphere of the moon or the planet that would be here. So this is really, or these are the main two reasons why Titan has such a thick atmosphere and why it's able to maintain it so well. So the reason number one being that the solar radiation is just not strong enough to break up nitrogen molecules, and also it's really far away from the sun. And two is that the actual molecule of nitrogen is heavy enough to be easily maintained by the gravity of this moon. However, it would most likely not be able to maintain oxygen for a very long time, specifically because oxygen would definitely be broken up without any magnetosphere. And at the same time, this actually creates a kind of a mystery and a kind of an unanswered question that we still haven't really been able to answer. Why is it that only Titan and Earth have such a thick nitrogen atmosphere? Where is nitrogen on Mars? Where is nitrogen on the other moons like Europa, Io, Ganymede, and Callisto? So why only these two objects in our solar system have nitrogen and have such a thick layer of it? And some scientists think that maybe it's actually because in the last few billions of years, both objects received a tremendously large collision from possibly some sort of a planetary body or a very, very large asteroid that delivered all of this nitrogen. And the other objects just didn't really get to receive that collision. But that's actually still not entirely proven or really has any kind of evidence, because we haven't really found these nitrogen asteroids or nitrogen planetary bodies. So for all we know, it could have actually been there from the beginning, and why, we don't really know just yet. But we do know that it's very, very important because nitrogen is absolutely essential for life, and it's basically one of the most important molecules out there. Both Titan and Earth got really lucky with the source of nitrogen. And it's also very possible that because of this, Titan has some really crazy mysteries on the surface, including potentially unusual life. But that's of course a story for another day. Anyway, so on that note, hopefully now you know a little bit more about why only Titan and Earth seem to have atmosphere and why other objects don't, and also why Titan has not lost its atmosphere even though it's been billions of years. For the most part, both planets will probably be able to maintain their atmospheres for quite a long time still, for as long as Earth maintains its magnetosphere, and for as long as Titan basically stays in the same region of space and the sun doesn't change too much. If one day Earth loses magnetosphere, it's probably going to also lose oxygen, but nitrogen is probably still going to be here. So the atmosphere of both of these objects is pretty safe. On that note, I think that's all I wanted to mention in this video. Thank you so much for watching, subscribe if you still haven't, share this video with someone who enjoys watching space videos, and maybe even consider supporting this channel on Patreon, because it does help me quite a lot. I'll see you tomorrow, space out, and as always, bye bye.